Alright, let's talk about Lab 1, constant velocity. The purpose of this lab is to analyze the motion of an object, in this case a marker, in motion with constant velocity. Because the marker has constant velocity by Newton's first law of inertia, it must also have zero acceleration. And because it has zero acceleration, the net force acting on the marker throughout the process must be zero. Some relevant formulas to this lab are the position update formula, which states that the final position is equal to the initial position plus the average velocity of the time interval times the amount of time passed in the time interval, and the velocity update formula, which says that the final velocity is equal to the initial velocity plus the net force times the time divided by the mass. So in this experiment, a marker was rolled in a straight line to measure its position and velocity at different timestamps. The timestamp of 0.033 seconds was chosen because of tracker, which I'll talk about later. The velocity of the ball throughout this experiment was 0.288 meters per second, and the initial position of the ball was at roughly negative 0.00460 with respect to the XY axis, which I'll also get into in a minute. The system of the lab is a marker, and surroundings is the floor they're rolled on, and friction and air resistance are to be ignored in the following computations. So the only force acting on the ball is the initial push, but nothing after that. So in configuring the axis through tracker, I chose to have the marker roll in the direction of the positive axis. It seemed more intuitive to do this, so I will have positive velocity and positive distance. Or positive displacement. It seemed a lot cleaner than the other alternatives, so the marker rolls towards positive infinity in this axis. In my computational model in Python, I was able to use the velocity and position update formulas. Here, if you check out this code, I tried to comment on it to make it clear. The initial position, as shown by the tracker, was at about negative 0.004600 with a velocity of 0.2888 meters per second and a timestamp of 0.033 seconds for delta t. So the while loop just shows that for the 1.467 seconds was chosen because that's how long the marker rolled in the screen for. And so while every timestamp under 1.467, the velocity of the ball was updated and the position was updated as well. So in this model, we have the observed model through tracker, and then the computational model through Python that I just talked about. And you can see that they are a little bit different. There is a discrepancy in between the two models. And as you can see, the predicted model is perfectly linear, as constant velocity should theoretically be. There is no change in the speed, so the change of position is constant. However, you could sort of see that while it's mostly linear, it starts to flatten out a little bit in the observed model, which is why it doesn't go as far as it is predicted. And that's probably because there is a net force in the form of friction acting against the marker as it rolled. So it had a negative acceleration, and therefore its velocity was slowing down. And with slowing down velocity, it did not travel as far as it would have if the velocity was constant. So what if we flip the axis? Well, this answer is simple. Position is a relative concept. If the axis was flipped, then the ball would have the same magnitude of its velocity, but it would be in a different direction. So the displacement would be negative, the velocity would be negative, but it would roll the same distance with the same speed. And is the zero net force justified? Well, no, because as we referred to on the graph before, the ball or the marker did not roll as far as we thought it would in our predictive model, and that's probably because of friction and that net force against it. And because there is this net force of friction against it, there must be some change in acceleration and therefore velocity. So it's not 100% fair to say that there is zero net force acting on this ball or marker. Once again, we made the assumption that friction was negligible, which in retrospect was not an assumption that we could make, but that's just one error of this computational model. However, maybe choosing a surface or a object with a lower coefficient of friction, or accounting in for friction into the change of velocity will be a more fitting experiment for next time.